I was looking at the history of science the other day, and I had this weird moment of, I guess, jealousy
Jealousy. Of whom?
of physics students. Or maybe it's sympathy for them, because if you study physics, it feels like all the giants have already walked the Earth.
Mhm.
Newton did gravity, Einstein mapped space-time.
Maxwell. Electromagnetism.
Exactly. It feels like the map is already drawn, and you're just, filling in the tiny details in the
We
corners.
feel like all the big earth-shattering discoveries are in the past.
Yeah. But then I started reading the material for this deep dive, and it suggests something completely different. The source material, that's a massive foundational text on artificial intelligence, it claims that AI is currently looking for, and I love this quote,
I think I know the one.
several full-time Einsteins and Edisons.
It is a great line, and it captures the reality perfectly. Physics might be a mature field, but AI, it's still the Wild West. It's not a solved puzzle. It's barely a sketched outline.
But that's what confuses me. If it's just starting, why does it feel like AI is absolutely everywhere right now? You can't open a browser without seeing it. So today, I want to cut through the noise. We're looking at the roots of the field to figure out what this beast actually is.
And that is a harder question than you might think. Because, spoiler alert, scientists still don't agree on a single definition of what AI is.
That was the first thing that really jumped out at me in the reading. I thought AI was just building smart machines. But the text lays out this grid, a 2x2 matrix of definitions. I found it really helpful, but I need you to help me walk through it.
Sure. It's really the best way to understand the fractured identity of the field. You have to make two choices to define AI. First, are you interested in the internal mind or the external behavior?
So, does it think versus does it act?
Exactly. That's
Yeah.
the first axis. And the second choice is, what's your standard of success? Do you want to simulate humans or do you want to be rational?
Rationality versus humanity, which, as anyone who has been to a chaotic family Thanksgiving knows, are definitely not the same thing.
They certainly aren't. And
Yeah.
depending on which box you tick in that grid, you get a completely different version of AI.
Okay, let's start with the one most people know. Acting humanly. That's the Turing test, right?
Right. Alan Turing, 1950, he proposed what he called an operational definition. He basically said, look, let's not argue about what thinking is. Let's just say if a machine can communicate via text and fool a human interrogator into thinking it's also a human, then it's intelligent.
And for a long time, I thought that was the gold standard. I mean, if I can't tell I'm talking to a bot, doesn't that mean it wins?
It means it wins at imitation. But our source material points out something fascinating. Modern AI researchers, they don't actually care that much about the Turing test.
Really?
It's just not the goal anymore.
Why wouldn't you want a machine that's indistinguishable from a person?
Well, think about aviation. For centuries, how did humans try to fly?
They looked at birds, they built wings that flapped. There is all that old footage of guys jumping off bridges with feather suits.
Right. They were trying to imitate nature. They wanted to fool the wind into thinking they were pigeons. And it was a total failure. We didn't get real sustained flight until we stopped imitating feathers and started studying, aerodynamics.
Ah, I see. So the goal isn't to make a machine that flaps its wings like a human brain.
Yeah,
It's to understand the aerodynamics of intelligence.
precisely. Aeronautical engineering isn't making artificial birds. It's making machines that fly. And AI isn't making artificial humans. It's making machines that solve problems.
That makes so much sense. And that leads us to the definition the source calls the winner. The focus shifted to acting rationally. This is the rational agent approach.
Yes, and a rational agent is simply something that acts to achieve the best outcome, or, to be more precise, the best expected outcome, given what it knows.
But why is that better than acting human? Wouldn't a perfect human simulation be rational?
Absolutely not. I mean, humans are terribly messy. We touch hot stoves even when we know they're hot. We procrastinate. We fail exams because we're tired or stressed.
Right.
If you build an AI strictly to mimic a human, you have to program it to make all those mistakes. You have to program it to get irrational or emotional.
So you'd be deliberately building a flawed machine.
Exactly. The scientific standard focuses on rationality because it's mathematically defined. It's generalizable. It's about the right answer, not just the human answer.
So we're moving from psychology, how people think, to engineering, how to solve problems in the best way.
You've got it. But to get there, we have to look at the foundation. And the deep dive into the history here was, well, surprising. I didn't expect to see Aristotle in a text about computer coding.
Yeah, that felt like a curveball. The text goes all the way back to Greek philosophy.
It has to. You can't have AI without the laws of thought. Aristotle wasn't just arguing for the sake of it. He was trying to formalize how we think. He developed syllogisms. Socrates is a man, all men are mortal.
Therefore, Socrates is mortal. I remember that from Philosophy 101.
But think about the implication. Aristotle showed that if you have the right premises, the conclusion isn't a guess. It's a calculation. It's automatic. And once you realize reasoning is a calculation...
You realize a machine might be able to do it.
Bingo. So that's the software. But you also need the hardware. And the source material does this comparison between the brain and the computer that, honestly, I had to read it twice. The numbers are just staggering.
It is a humbling comparison for computer scientists. If you look at raw speed cycle, time computers win easily. A transistor flips millions of times faster than a neuron fires in your brain.
So technically, computers are faster thinkers.
Faster processors.
Right.
But the brain has a secret weapon. It's not about speed, it's about connections. A typical computer CPU does one thing at a time, just incredibly fast. It's serial.
But the brain, it has 10 to the 11 neurons, 100 billion.
Okay, that's a big number, but a hard drive has billions of bits.
But wait, those neurons are connected by 10 to the 14 synapses? That's 100 trillion connections.
I can't even visualize that number.
Think of it this way. A computer is like a Formula One driver, extremely fast, but alone on the track, doing one lap after another. The brain is like a billion people whispering to each other all at once. That's why you can look at a crowd and instantly recognize your mother's face.
Right, that happens in a split second.
For a computer, that is an incredibly hard problem. It has to scan pixel by pixel, line by line. The brain does it by massive parallelism. It's just a totally different architecture.
So we're trying to build intelligence on a machine that fundamentally works differently than the only intelligent thing we actually know as.
Which explains why the early days of AI were so optimistic and why they hit a wall so hard.
Let's talk about those early days, because the birth of AI as a field has a very specific date. Summer of 1956, Dartmouth College.
The legendary workshop. This is where John McCarthy coined the term artificial intelligence. You had Marvin Minsky, Claude Shannon, Herbert Simon. I mean, the absolute giants.
And the proposal they wrote for this workshop is, looking back, it's hilarious. I have to read this quote. They proposed a 2-month, 10-man study based on the idea that, and I quote, every aspect of learning can be so precisely described that a machine can be made to simulate it.
They really thought they could make a significant dent in the problem of creating a mind with 10 guys in one summer.
It's the ultimate hold my beer moment in science.
It really was the look ma no hands era. And to be fair, they did pull off some miracles. In the years right after that workshop, they had computers proving logical theorems. There was a program called The Logic Theorist that proved a theorem from Principia Mathematica more elegantly than the human authors did.
And Arthur Samuel's checkers program? The text says it learned to play well enough to beat its own creator. That must have been a spooky moment in the 50s.
It was huge. It disproved the idea that computers can only do what they're told. Samuel didn't tell it how to win. He told it how to learn. Herbert Simon was so hyped he predicted in 1957 that a computer would be chess champion of the world within 10 years.
Spoiler alert, it took 40 years.
Right. And that gap between 10 years and 40 years. That's where the trouble started. That leads us to the first AI winter.
The text mentions that a lot of the failure came down to microworlds and something called combinatorial explosion. Can we unpack that? Because combinatorial explosion sounds like a bad action movie.
It's the reason why things that are easy for humans are so hard for computers. The early AI programs worked great in these micro-worlds, very simplified simulations. Imagine a world with just 4 blocks on a table. The computer could say, pick up the red block and put it on the green one. Easy.
Okay, so why does that fail when you try to apply it to the real world?
Because of the explosion of options. Imagine a small maze. A computer can check every single possible path in a fraction of a second to find the exit.
Sure.
But if you just add a few more squares, the number of possible paths doesn't just double, it explodes exponentially. If you try to model the real world, the number of possibilities becomes greater than the number of atoms in the universe.
So the computer tries to check every option, like it did in the micro world.
And it freezes. It would take millions of years just to make the next move. That is the combinatorial explosion. Real life is just too big to search through.
There's a great anecdote in the notes about how this misunderstanding played out in machine translation. During the Cold War, the U.S. government was desperate to translate Russian scientific papers.
Oh, this is a classic. They thought translation was just swapping words. Look up the Russian word, find the English equivalent, swap it.
A simple substitution?
But without context, it's a disaster. The famous story is they tried to translate the biblical phrase.
The spirit is willing, but the flesh is weak.
That's the one. They fed it into Russian and then back to English.
And what did the machine spit out?
The vodka is good, but the meat is rotten.
Oh, no.
I mean, it's grammatically correct,
Eh.
but semantically, it's a catastrophe.
So the government sees vodka and rotten meat and says, we're wasting our money.
Basically. In 1973, the Lighthill Report came out in Britain, just criticizing the field for failing to handle this explosion of complexity. Funding dried up. AI became a dirty word for almost a decade.
But obviously, we're here talking about it, so it didn't die. It came back with something called expert systems.
Right. The field lowered its sights. They realized to solve a hard problem, you can't just use pure logic. You need to know things. You need specific knowledge.
So instead of a general thinking machine, you build a machine that knows everything about, say, molecules.
Exactly. That was DNADRL, a program to infer molecular structures. Instead of trying to derive the structure from raw physics every time, they programmed it with cookbook recipes from actual chemists.
And then there was MyCIN for blood infections?
MyCIN was incredible. It used about 450 rules acquired from expert doctors. If the patient has a fever and this test is positive, then check for this bacteria. It actually performed better than junior doctors at diagnosing blood infections.
That feels like the first time AI was actually commercially useful.
It was. By the late 80s, companies like DEC and DuPont were saving millions using these systems. But they were brittle. You had to hand code every single one of those rules.
Right, and that's not how ChatGPT works today. That's not how a self-driving car works. You can't write a rule for every pothole in the world. So when did the data take over?
That's the modern revolution. And it's a shift from asking experts to using the scientific method. Instead of just asking a doctor for a rule, researchers started using probability and statistics on massive amounts of data.
Big data.
Huge data. And there was a specific study mentioned, Banco and Brill in 2001, that I think just sums up this entire revolution.
This was the confusion of tongues study.
Yes. They wanted to test different algorithms for understanding language. They took a dumb algorithm, simple, nothing fancy, and gave it 1 billion words of data. Then they took a genius algorithm, highly sophisticated, the best code available, and gave it only 1 million words.
So the genius student with a pamphlet versus the average student with a library, who won?
The average student with the library destroyed the genius every single time.
That is a wild insight. We spent decades trying to write better, smarter code when we should have just been reading more books.
Exactly. It turns out that for many problems, data isn't just fuel, it is the solution. Google didn't win search because they had better code than everyone else. They won because they had the entire internet to learn from.
And this explains the photo completion example, too. Hayes and Efros.
Right. They tried to write a program to fill in holes in photographs, like if you cropped someone out of a picture and wanted to fill in the background. With 10,000 photos, the results were terrible. But when they scaled it up to 2 million photos...
The results were excellent.
Excellent. The computer just found a similar photo in the database and pasted it in, effectively. It stopped trying to understand what a tree looks like and just found 1 million examples of trees.
So we've gone from Greek syllogisms to the optimism of the 50s, through the winter where logic failed, to this spring of data-driven success.
And that brings us to today. We have robotic cars like Stanley, which won the DARPA Grand Challenge, not by thinking like a driver, but by calculating probabilities of the road surface hundreds of times a second. We have Deep Blue beating Kasparov.
And logistics. The source mentioned the DART system used during the Persian Gulf crisis.
This is one of those invisible successes. They used AI to plan the logistics for 50,000 vehicles, cargo, and people. DARPA stated that this single application paid back their entire 30-year investment in AI.
Wow.
All those years of funding paid off in one operation.
So drawing this all together, the takeaway I'm getting is that AI isn't magic. It's not even really psychology anymore.
No. It's a mix of science, engineering, and mathematics. It has evolved from trying to rebuild the human brain neuron by neuron to building systems that act rationally based on massive evidence.
It's not about making a machine that feels like a human. It's about making a machine that does the right thing.
Exactly. But, and here's the final thought to leave you with, the source brings up the concept of the singularity.
That's the sci-fi concept, the point where computers get smarter than us.
Right. And we have raw computing power now that rivals the brain in terms of operations per second. We have the data,
Yeah.
but we still don't know how to achieve the brain's level of general adaptability. And it raises this really haunting question.
What's that?
By feeding these machines all of our writing, all of our photos, all of our data, are we actually building a mind? Or are we just building a really, really efficient mirror that reflects our own data back at us?
That is something I'm going to be thinking about all day. Are we building a mind or a mirror?
It's the ultimate question.
Thank you for helping me unpack this. This has been The Deep Dive.
Thanks for listening.